started again. So I just wanted to remind you where we left off. So we just finished covering the sum check protocol. And this allows a prover and verifier to compute the sum of an L-variate polynomial's evaluations over all 2 to the L Boolean inputs. And the verifier's runtime is order d times L, where d is the maximum degree of the polynomial in each variable, plus the time required to evaluate that polynomial g at a single point. And we should compare this like one last time to the time required to just solve the problem in the first place. And that time is at least 2 to the L times the time required to evaluate g at one point. Right? Because the function we're trying to compute here is summing g's evaluations at 2 to the L inputs. We basically turned 2 to the L evaluations of g as far as the verifier's runtime goes down to 1 evaluation of g. All right, so now we're going to see why this protocol is so useful. So I'm going to give an interactive proof for a problem called Sharpset. All right, so in this problem, the input is a Boolean formula. Let me call it phi. I'm going to let s denote its size and n the number of variables. Okay, so a Boolean formula is just its inputs are 0, 1 valued. And then the formula consists of AND, OR, and NOT gates. And formula just means each gate has fan out 1. Right? So each gate has one wire coming out of it. Right? So this Boolean formula just computes some function of the inputs by applying these logic gates to the inputs.
So each input appears only once there? Is that just because the diagram's simple? Or is
well, when each, it's a formula, so each gate has fan out 1. So like, even the inputs can only...
I mean, like, could X3 be the input to multiple gates?
Oh, I see. Yeah, it could be. It could be. Okay, other questions about Boolean formulas? Okay, so it'll be important that each gate has fan out 1, but this is just a picture. It's not, don't overfit to the picture. X3 could also be fed into another gate. Okay, so the goal is to count the number of satisfying assignments of the formula. So that is the number of assignments that cause the formula to evaluate to true. So put another way, if we view the formula as a function mapping n bits, 0, 1 to the n, to bits, 0, 1, where we're interpreting 0 as false and 1 as true, then we're just summing up phi's values, the formula's values on all Boolean inputs. Does the problem make sense? Okay, so that is our goal. And this should kind of look a little familiar because we're summing up some function's values over all Boolean inputs. We've seen something like that recently. So before I tell you how to solve it, let me just make sure everyone is clear about what I mean by this being a 0, 1 valued function. So let me just evaluate this formula on a certain 0, 1 valued input. So this is a NOT gate. So NOT of 0 is 1, right? NOT just negates the false to true and true to false. And then this is an AND gate. So if you feed 2 true values into AND, it evaluates to true or 1. And this is an OR gate. So OR of true and false is true, and then the output of the formula is true in this case. Okay, so we want to sum up the 0, 1 valued function on all Boolean inputs. And this is how we do it. We just apply the sum check protocol to an extension of this formula, an extension polynomial. So that is, we let g be any polynomial such that if you feed into g a Boolean value, it spits out exactly what phi spits out on that value. And the sum check protocol lets us sum all of that up. Does that make sense? So hopefully if sum check seemed esoteric originally, why would you want to sum up the evaluations of some polynomial on a bunch of inputs? Now it seems less so. All right, so why aren't we done? Like, why don't we just move on to the next application? And the answer is we need some properties out of this polynomial g. So firstly, in the final round of the sum check protocol, the verifier has to evaluate the polynomial at a randomly chosen input. So we better choose an extension g of phi for which the verifier can evaluate g efficiently at a randomly chosen input. And we need more from G, so we need it to be low degree. Right? So to control the soundness of the protocol, to control the prover's runtime, the length of the messages, and thereby the verifier's runtime, everything depends on G being low degree. If G had just huge degree, everything's going to go out the window. Right. So the next few minutes are going to tell you how we can take this formula phi and turn it into a extension polynomial G.
Sorry, do you know that F is low degree? Like if input x3 had been going to like 1,000 different gates, would that be a low degree polynomial still?
So the formula phi is not a polynomial at all. It's just a Boolean formula. So I'm not sure your question is quite well defined.
I see.
So we just have to take this Boolean formula. Formulas have nothing to do with polynomials. And we have to turn the formula into an extension polynomial.
Okay, so you're about to tell us how to do it.
Yeah. So that's what the next few slides are going to be about.
There's no F here? Like before the extension polynomial G was defined, but there's no
Right. Yeah, so the F from the previous hour that we were talking about extensions of is this phi when viewed as a function on 0, 1 to the n to 0, 1. So this phi is that F. Okay. But that F was not a polynomial or anything. It was just a function from 0, 1 to the n to 0, 1. And we now need to come up with an extension polynomial of that function. Other questions?
Why is this an extension?
So I haven't. I think you're asking why is it enough to have an extension polynomial?
No, well maybe that too, but I guess it seems like it's the same kind of size. It's the picture you gave. The extension seemed like there was a lot more of inputs mapping. So
Yes.
I'm just missing that here.
Yeah. So right. So we are not going to use so that picture. No party is going to materialize that whole picture. So you're right. That picture, like the polynomial, had this huge domain. Right. The domain of G is field to the n. That's a huge domain. So not even the prover is going to materialize that whole domain. Right. So in order to apply the sum check protocol to a polynomial, it's just important that the prover and verifier be able to evaluate the polynomial efficiently at any desired point. That doesn't mean they have to evaluate it at every single possible input. But the other interpretation of your question is also worth addressing. So the reason it's enough to compute the sum of an extension polynomial of phi's evaluations on the Boolean inputs is an extension polynomial by definition agrees with the thing it's extending at the Boolean inputs. So we really care about this sum, summing phi's values at the Boolean inputs. But an extension is going to spit out the same things on those Boolean inputs. So by replacing phi in the sum with the polynomial, we're not changing the sum. That's essential. Any other questions? So to summarize this protocol, all we're doing is we're applying the sum check protocol to an extension polynomial of this 0, 1 valued function phi. But in order to fully specify the protocol, I have to tell you how exactly this extension is defined to ensure that it's low degree and the verifier can evaluate it efficiently at a point. Okay, so yeah, that's the key question. And the way you do this is a technique called arithmetician. Right. So this is what arithmetician does. So it replaces the Boolean formula phi, whose gates are and, or, and not, and it turns it into what's called an arithmetic circuit. So an arithmetic circuit is a circuit whose inputs are entries of a finite field, and whose gates compute addition and multiplication over the field. And what this arithmetic circuit is going to do, the way we get it, is we replace each Boolean gate of phi with the multilinear extension of the function computed by that Boolean gate. Okay, so let's see a picture of this. So that's what we've done here. So what is the multilinear extension of the not function? So not maps 0 to 1 and 1 to 0. So there's a unique multilinear polynomial that does the same thing, and that is just 1 minus the input. Right? This 1 minus 0 is 1, and 1 minus 1 is 0. Yep.
Sorry, I guess I don't want to keep harping on this point, but But there's something I'm not getting intuitively, which is like if like x3 were like fanning out to a whole bunch of things,
Yeah.
why don't you end up getting a high degree?
Yeah, so yeah, I will come to that, but basically, when we turn this formula, and this is why a formula is important, when we turn this formula into this arithmetic circuit, it turns out it's not so hard to see that the degree of the polynomial computed by this arithmetic circuit is at most the size of the formula. So if x3 fed into many different gates, well, each thing it feeds into is contributing to the size S of the formula. So that gives us, so we're allowed to use a higher degree polynomial here because the degree of this is, we're going to let it be as big as the size of this. That makes sense?
It's worth to point out this very same fact is not true about circuits.
Right, so yeah, so okay, so to dive into the weeds quickly, so Ali is pointing out that this fact is not true about circuits. We're really using formulas here. Imagine like the circuit that computes the end of n bits by a binary tree of like fan into n gates. Not a binary tree. I'm not sure I can actually come up with this online. I think there's a very small circuit for like the end of n bits, like has size. Is this through? Can you help me with this online?
You can consider, for instance, an exponentiation.
Repeated
like
squaring
this.
then.
Yeah, that's what I'm trying to get at with like an end of, so n turns into multiplication, so I'm trying to do repeated squaring in the Boolean. Yeah, okay, so yeah, I'll try to come up with this answer maybe if there's extra time at the end. But it's really important to make sure that the degree of this is at most the number of gates in the formula. It's important that it's a formula that is everything is fan out 1.
If you write wi is equal to the end of wi minus 1 with itself, and you do arithmetization, it will have exponential degree.
Yeah, that seems right. So that you can take the, yeah, so I guess that's computing the end of like one thing. Yeah, it's a stupid way to compute the dictator function, which just spits out the input. And if you were to arithmetize that circuit, you would get a very high degree polynomial. Yeah, we talk offline. Okay, so what this transformation is doing is it's replacing not x with 1 minus x. It's replacing end of xy with x times y. Right? Because end evaluates to true only if both of its inputs are 1. And this multilinear polynomial evaluates to true at 0, 1 valued inputs only if both of them are 1. Right? If either one of these is 0, it's 0. And this is the multilinear extension of OR. So you can think about this all, there are only 4 cases to check, right? So 0 maps to 0, and any other 0, 1 valued string maps to 1. So this transformation is going gate by gate through the formula and replacing the gate with the multilinear extension. So the NOT gate turned into 1 minus the input to the NOT gate. Times, n turned into times, right? This OR gate turned into this thing that sums its 2 inputs and then subtracts the product. So this summed the 2 inputs and this subtracts the product. Okay, that's the transformation. And it should be clear, I think, by examining this, that this is indeed an extension polynomial, this arithmetic circuit. Just because, like gate by gate, as you work your way through the formula, the same kind of thing is happening in the polynomial world as long as your inputs are Boolean. So let's actually see that on an example. So if you evaluate the formula gate by gate on this example, like the NOT gate evaluates to 1, and this arithmetic gate also evaluates to 1. Similarly, the AND gate evaluates to 1 because it's 1 times 1, and this times gate, or 1 and 1, and this times gate is 1 times 1. So the same thing is happening on both sides. Right? That OR gate evaluates to 1, and so does this minus gate that's computing the multilinear extension of OR. So just gate by gate through the whole circuit, it's preserving what the formula is doing. Okay, but this arithmetic circuit is computing a polynomial. Is that clear? So arithmetization is one of the most powerful ideas in complexity theory. It's a way to kind of go from Boolean functions which have nice representations into kind of algebraic encodings of those functions, interpreting them as polynomials. Okay, so to summarize, this is a technique for turning Boolean formulas into arithmetic circuits. And yeah, if you do, so I guess I can say a little bit about this fact. So if the formula has size s, the degree of the polynomial computed by this circuit is at most s. And that's true basically because we use multilinear extensions here. So like for each gate in this circuit, like this AND gate is the product of two inputs. And that product of two inputs is a multilinear function. So whatever the total degree of this thing was feeding into the AND gate and this thing feeding into the AND gate, the AND gate itself is just turning into the product of those two things, right? So if you work through it, that's how you get the degree bound. You know, each gate in this formula is kind of contributing to the degree of the resulting arithmetic circuit. And moreover, this is the easiest thing to see. The arithmetic circuit can be evaluated at any input in time order s. And that's because each gate of the formula is turning into a constant number of gates in the circuit. Right? So to like evaluate this OR gate was just one step here, and here it's like 3 steps, because you do one addition, one multiplication, and one subtraction. And again, each field operation I'm calling just one unit time step. Questions about arithmetization?
Do you know who and when came up with this? Sorry.
There's certainly people in the so this protocol for Sharpset is from Lund, Fornau, Karoff, and Nissan. There are dozens of people in the room who can tell me whether arithmetization originated in that paper.
Maybe Lipton?
Yeah, Lipton, Beaver, Feigenbaum, we don't know who.
I think Lipton was older than the paper.
Yeah, so there was a sequence of works where these ideas were developed and refined and built on, and you can trace them.
Not for this purpose. For this purpose, see if you quote it.
Mm-hmm.
Thank you.
Okay, other questions? Okay, so if there are no more questions, then we can summarize. So the Sharpset protocol simply applies the sum check protocol to the polynomial g computed by this arithmetic circuit. That's it. The very end of the protocol, the verifier has to evaluate this polynomial at a random point, and it can do it just gate by gate through the circuit. All right, so to summarize the cost of the protocol, this is an n-variate polynomial we're applying sum check to, so there are n rounds. The degree of the polynomial we're applying sum check to is s, where s is the formula size. So this means that the total communication and verifier runtime turns out to be bounded by s times n, the number of inputs to the formula. So note, like even for the verifier to even read the formula, it takes time s. So this is only a factor n off from optimal. And the prover time, and I didn't go into the details of this before about how you achieve this, but the prover can be made to run in time s times n times 2 to the n. And in some sense, this is also optimal. Certainly, we do not know a faster algorithm to even solve the problem than about 2 to the n time, actually s times 2 to the n time. Right, it's not clear how to solve the problem other than more or less for the prover to evaluate the formula on every possible input. There are 2 to the n inputs. Each one might take time s to evaluate the formula n. So that's the protocol, and up to like this factor n here, like every party is running optimally quickly. Okay. So that's the Sharpset protocol. Now Sharpset is it's called a sharp p complete problem. Exactly the definition of that isn't so important, but this is considered like a very big class of problems. It's a powerful class. And because we can solve Sharpset, we can actually solve any problem in that class. And in fact, it's not too much harder to show. This was your question from before about IP equals P space. This is already like the technical core of the following result. It's a famous result of Shamir building on the LFKN paper. So any problem solvable in polynomial space has an interactive proof where the verifier runs in polynomial time. And the technical core of that result is actually the Sharpset protocol. Okay, so that's a wonderful result. You can ask, is this a practical result? Can we use it for anything? And I think the answer is that it is not a practical result, and I'll explain why in a moment. The main reason being the runtime of the prover. Okay, so what's going on here? So, I said that the prover runtime in the Sharpset protocol is basically optimal because we can't even solve the problem. We don't know how to solve the problem in less than 2 to the n time, and the prover is running in close to 2 to the n time. But in the real world, are people really solving problems that take 2 to the n time to solve at all? I don't even think like Google's cloud computer or whatever company can really solve piece-space complete problems if they're truly like adversarial instances and large instances. So what we'd really like is to apply these techniques to solve problems that people can solve in the real world. And you can try to do this by kind of taking your easy problem and turning it into a Sharpset instance and then running the Sharpset protocol on that Sharpset instance. That's like a crazy way to try to solve your problem, but you could do it. And if you try to do it, you'd run into this issue that the prover would run in super polynomial time, even if the problem you started with was very simple. So in principle, you can take any problem solvable in logarithmic space, you can turn it into a Sharpset instance, and you can apply the Sharpset protocol to that Sharpset instance, but the prover will still run in super polynomial time on that Sharpset instance, even if your original problem was solvable in logarithmic space, which is a very simple kind of problem. Okay, so I want to be clear, like you can't really improve the Sharpset protocol kind of on its own terms, because the problem takes time 2 to the n to solve anyway, even without a guarantee of correctness. But what you can do is you can hope, if you started with an easy problem, but one that the verifier wants to outsource anyway, you can hope to do better than what you would get by applying the Sharpset program to that easy problem. Does that make sense?
I guess I'm confused. You said that if you start with something that's log space, then n is log n, right? So then.
Yeah, so if you start with a problem that's solvable in log space, you can turn it into a Sharpset instance where the number of variables of the Sharpset instance is log squared n.
Okay.
I'm not going to tell you how to do it. It's something like Savage's theorem or something. And but then if you apply the Sharpset protocol to that, that takes time 2 to the log squared n, which is super polynomial. Yeah, so we really want like a more direct way to solve easy problems. Right, this is a great protocol, but it only applies to a hard problem. So let me tell you what our new goal is. Our new goal is captured by this notion called doubly efficient interactive proofs. And we'll see what that means in a second. So what we really want is we want the verifier to not do much more work than just read the input. So we want a linear time verifier. Okay, and we want the prover to run in polynomial time. Right, so of course, we can't even hope for this if the problem we're outsourcing to the prover is not solvable in polynomial time. But imagine the problem we're outsourcing to the prover is solvable in time n to the 4th. And the verifier doesn't have the resources to run in time n to the 4th. This protocol will be useful. A doubly efficient interactive proof will let the verifier basically just read the input. That's it. And the prover will still be efficient. We'll run in polynomial time. Does that make sense? So this is the sort of thing we actually care about in this program this semester. Right? We don't want our provers to run in exponential time. OK, so I want to give you a very clean example of a doubly efficient interactive proof for a problem counting triangles, which people actually do care about. And the main point of showing you this protocol actually is just to show you that the sum check protocol is like really useful. I think for a long time, people thought this is a beautiful protocol for Sharpset, but this is not a useful thing. Sum check was the key to it, but sum check isn't that useful. Hopefully, within one more slide, you'll appreciate just how powerful the sum check protocol is, and it's also just kind of a cute result. OK, so counting triangles. Our input is the adjacency matrix of a graph. So that's an n by n matrix whose entries are 0, 1. So 1 represents there's an edge between these two nodes, and 0, there's no edge. OK, so counting the number of triangles in the graph is the same as computing this sum. OK, so this is saying you're summing over all triples of nodes I, j, and k, and asking, is there an edge between ij, jk, and ik? That's what it means for there to be a triangle between I, j, and k. They're all connected to each other. And this 1/6 here is just because there are 6 ways to order I, j, and k, and you don't want to count the same triangle 6 times. So the fastest known algorithm for this problem, much like in Frivold's protocol, runs in matrix multiplication time, which is currently not known to be n squared. It's bigger than that. So I'm going to give you an interactive proof for this problem, and it'll be doubly efficient. So the verifier will run in linear time, that is n squared time, and the prover will run in polynomial time. So this is how it works. The one tricky thing here is we're not going to view the input as an n by n matrix. Okay, we're going to view the input as a function on 2 log n bits in the natural way, but in case you don't think it's natural, let me explain that. So we're going to interpret the first log n bits as specifying a number I between 1 and n, and the second log n bits as specifying a number j between 1 and n. And we're going to interpret a as a function as spitting out just aij. Okay, but the inputs we're thinking of as bits instead of indices between 1 and n. That makes sense? Okay, so now we have our input is no longer an n by n matrix. It's actually a function on 0, 1 to the 2 log n. And that's the kind of functions that we've talked about taking low degree extensions of. So we're going to let a twiddle denote the multilinear extension of that function. And I'm going to define this polynomial here. So it's just the multilinear extension of the input evaluated at variables x, y times the same thing, but now with the variables y, z, and times the variables x, z. Okay. So now like a twiddle has degree at most 1 in each variable. This thing has degree at most 2 in each variable, because like each coordinate of x appears twice. Each coordinate of y appears twice, each coordinate of z appears twice.
So if you have like a self loop, that counts as a triangle? Or?
Let's say there are just no self loops in the graph. let's just, however you want to define it so that this is the sum I want to compute. Okay. Okay. Other questions at this point?
So there's nothing special here to 3, right? You can apply to counting k-clicks.
Correct. Yeah. Yeah. So this is quite a general technique. Actually, you can count like arbitrary subgraphs, but it's just cleanest to talk about triangles.
And how does the upper bound using matrix multiplication scale with k?
That I don't know. I'd have to think about that offline. Okay, so the final protocol is we're just going to apply the sum check protocol to this polynomial. So the point is that this polynomial extends this function here that we're trying to sum. Right, so this is very similar to the Sharpset protocol. I mean, it's basically the same thing. It's just the polynomial we're applying sum check to is different.
If you wanted a simpler solution, I mean, you said this is going to make us appreciate this check and sum check, but because the optimal or best algorithm is running kind of matrix multiplication, it means that we could use your other protocol at the beginning of the talk as well. Yeah.
Yes, so that's a great question. So because there is an algorithm so the question was, can you solve this problem just using a matrix multiplication protocol because you can count triangles with matrix multiplication? The answer is you can, but in that protocol, the matrix multiplication protocol, the prover had to send the actual product matrix. Okay. And that would be n squared bits. And the total communication of this protocol is going to be like order log n. So this is kind of the magical power we see interaction buys you, is it kind of can force, the verifier can force the prover to materialize a bunch of values without making the prover actually send those values to the verifier. So if you use something non-interactive like Frivold's protocol, well, Frivold's is great, the verifier's linear time, but the prover actually has to send all of these values to the verifier. Other questions? Okay, so yeah, so again, the protocol just applies sum check to this 3 log n variate polynomial. What are the costs? So because g has degree at most 2 in each variable, and there's only logarithmically many variables, the total communication is only logarithmic. The verifier just has to evaluate the multilinear extension of A at 3 points, and I mentioned in the last hour, the previous hour, that each of those evaluations can be computed in linear time, n squared time. So the verifier just runs in linear time, exactly as we wanted. And the prover's runtime is not much more than just what's required to compute this sum in the first place in the naive manner anyway, which is n cubed. And I'll just mention if you're more clever about it, you can actually come up with a different protocol where the prover runs in matrix multiplication time as well. But you have to change the protocol.
What's the best deterministic time for counting triangles?
Yeah, I think it's matrix multiplication time. If you just want to solve the problem.
That's the best.
Yeah. Right. Which is more than n squared. So we're saving the verifier time here.
So this seems to be a log n round protocol. For this problem, do we know even constant round protocols which are doubly efficient?
Yes, but the communication is going to blow up to a polynomial, but the polynomial can be arbitrarily small as long as your constant is arbitrarily big.
That's basically instead of log. You're going from 0, 1 to the log n, you're going to take some field to the...
That's right. Or some subset of the field to the less than log n. Yeah. So you can play games with this if you wanted to. And to play these games, to trade off between rounds and communication, you no longer work over 0, 1 to the L. You work over some other product set.
You said you can reduce the prover's complexity to the matrix multiplication. What would be the trick?
Yeah, so the key to that is to use a non-trivial, an optimal interactive proof for matrix multiplication. Right, so Freerod's protocol, again, is optimal in a certain sense because the verifier is linear time, but the prover actually has to send the product matrix. And there's a known interactive proof for matrix multiplication where if you don't actually care about the product matrix, there are ways to avoid the prover actually sending it explicitly. So I probably want to leave it at that unless there happens to be lots of extra time at the end of the talk. But does that give you an idea?
But then you don't use sum check.
No, you still use sum check. But so basically, you replace Freerod's protocol with a sum check-based interactive proof for matrix multiplication. And it's a non-trivial, I mean, it's my protocol, so I don't want to talk it up too much, but I like it. It's non-trivial. Yeah.
Can you repeat what did you say were the parameters if you wanted to make it constant round?
Yeah, so I think it should be, so if you interpret, rather than viewing A as a function from like 2 log n bits to 0, 1 or the field, if you instead view A as, say, a function from 0, 1 up to n to the 1/4 by 0, 1 up to n to the 1/4, and you do that 4 times, you can still define low degree extensions of that, that function, which is now only like a 4-variate function or 8-variate or whatever. But your communication is going to grow like n to the 1/4 rather than log n. And what's happening is as you try to drive the number of variables down, you blow up the degree of the extension. So within sum check, you're cutting down the number of rounds, but increasing the amount of the degree of the polynomials that the prover has to send in each round.
And would you say this is probably the best we know for constant round?
I believe so.
And to the 1 over C, like we could do any.
I think so. I know that Rothblum and Goldreich have some recent work on, interactive proofs for simple problems, and I'm not sure if they might have an interesting result in there, but if I had to guess, this is actually optimal, so that is speculation.
It also increases the running time of the verifier, because you need to sum up over on the...
Correct, but in a doubly efficient interactive proof, we just require a linear time verifier, so as long as these polynomials are at most degree n, and all of them will be, we're not violating the doubly efficient interactive proof property. But you might be driving your communication up closer and closer to linear in n. Any more questions?
But By optimal, you meant what among the best we know, not that.
Yeah. Well, it's possible that the problem's just solvable in linear time, and then there's no communication. And
No, so we know something that if it's solvable with log n and constant round, matrix multiplication is faster.
I don't think we know anything like that.
Okay.
People will study settings, interactive proofs with restricted verifiers, like a verifier that has to be a streaming algorithm. And in that setting, we know that this protocol is optimal in some sense or close to optimal. But yeah, for general verifiers where computation is the bottleneck, obviously I don't think we have results there.
So maybe this is orthogonal, but let's say that the verifier should run in sublinear time, and it's kind of like this public testing. Mm-hmm. That's something similar too?
I would have to think about that. Yeah, I don't know. I'll take that offline. Yeah. Any more questions? Okay, so anyway, I think the main point I'm trying to convey here is just that a lot of problems, even problems people really care about in the real world, turn out they can be phrased often in non-trivial ways as just a big sum. And oftentimes each term of the sum agrees with some low-degree polynomial. And if you have that situation, then as long as the verifier can evaluate that polynomial efficiently at a random point, just apply some check to it. And you'd be surprised how far that can get you. Okay, let's see. 20 minutes left? I'm really bad at analog time. I think it's 20 minutes. That's good. Okay. All right, so I want to talk about general purpose, doubly efficient interactive proofs. And from now on, I can necessarily only be quite sketchy in how they work. But I want to tell you the main results. Because these are the frontiers both for open research directions and just the things people are using in practice now a lot. So what do I mean by a general purpose, doubly efficient interactive proof? Well, ideally we would like an interactive proofs that kind of apply not just to counting triangles or matrix multiplication, but you can kind of apply them to any problem. All right, so the first general purpose, doubly efficient interactive proof I want to tell you about is a result by Goldwasser, Klei, and Rothblum from 2008. And this it applies to any problem, but it's only efficient, it's only doubly efficient if the problem is solvable by a parallel algorithm. So let me explain. So general purpose proof systems ideally work as follows. So you'd like the verifier to be able to say, here's a computer program I want the prover to run on my data. And the way these proof systems tend to work is the first thing they do is they say, well, computer programs, I don't really know how to deal with them. I'm going to turn the computer program into some other representation of the computation, which is easier for me to deal with. And normally this kind of representation is an arithmetic circuit or something similar. So we already saw arithmetic circuits in the Sharpset protocol. Right, so you've basically already seen this sort of thing. We don't like Boolean formulas, so we turn them into an arithmetic circuit computing a low-degree polynomial. So typically, we call these kind of programs to circuit transformations. We call them like the front end of the system. And then we design the interactive proof to work on the circuit. So we make sure the prover actually correctly evaluated the circuit gate by gate. So that's how the GKR protocol works. So it operates on a circuit, an arithmetic circuit. Okay, and the protocol will be efficient as long as the circuit has low depth. Okay. And it's just a fact that I won't go into any detail about, that if your computer program actually implements an efficient parallel algorithm, then the circuit that comes out of the front end can be made low depth. So like the depth of the circuit is like the number of sequential steps that the parallel algorithm runs for, roughly speaking. Right, so the GKR protocol just tries to verify that the prover correctly evaluated the circuit gate by gate. And I'm just going to give you like a caricature of how it works. I obviously can't give full details about it. So I would like to compare it to like the world's dumbest proof. So the world's dumbest proof, I think, would work as follows, at least the most convenient dumb proof. So the dumb proof would start by the prover just saying, hey, this is the output value of the circuit. So here's the output gate, this is what it evaluated to. Now the verifier doesn't believe it. So the prover can say, well, look, I'll prove to you that this output gate was evaluated correctly. Here are the inputs to the output gate. Go check for yourself. Like, I'm telling you the truth about these inputs, so just make sure that the value of the output gate is actually the sum of these two inputs. And the verifier could do that, but then the verifier is like, well, obviously if I didn't believe you about the output gate, I don't believe you about these things. So the prover's like, no problem, I'll send you the values of all the gates feeding into those things. And they can keep doing this until eventually the prover gets to the input level, and the verifier sees the input explicitly, so the verifier can just check, does what the prover's saying the input is actually agree with the true input? Great, all right, so we're done, right? So the problem, of course, here is that this is as expensive, even in just the communication, much less the verifier time, as just the verifier evaluating the circuit herself. So what we really need is a way to kind of do this sort of walking from the output to the input level without actually having the prover materialize all the intermediate gate values to the verifier. So that's what the GKR protocol does. And I can't really give much more detail than that in this talk. But basically, what they do is, so first the prover sends the claimed output of the circuit, and then they invoke the sum check protocol, applying it to like a very cleverly chosen polynomial. And at the end of that sum check protocol, the prover is basically forced to make a claim about the value of that polynomial at a random point. And because of the way that polynomial is defined, it's like turns out to be defined in terms of the gate values at this layer of the circuit feeding into the output. That is implicitly the prover making a claim about the gate values at this level. Okay, but it's the sum check protocol only has logarithmic communication, right? So somehow, conceptually speaking, the same thing happened in the dumb proof as in the GKR protocol. But in the GKR protocol, we've avoided the need for the prover to actually send all of the claimed gate values at this layer to the verifier. Of course, at this layer, there are only two gate values, but eventually you're going to get to a really wide layer, and that's where the savings really come in. Okay, so hopefully this is making a little bit of sense, giving you some idea of what's going on. But to summarize, at the end of this first invocation of the sum check protocol, the prover and verifier have reduced a claim about the output gate to the circuit to a claim about the gates feeding into the output. In the sense that if the verifier believes the claim about these gates, it's safe for the verifier to believe the claim about these gates, the output gates. Okay. But they did this somehow without the prover actually sending all of these gates to the verifier. And they just do this round by round, kind of reducing a claim about these gates to a claim about these gates until they eventually get to the input. And when they get to the input layer, what the prover has actually done is the protocol, much the way we interpreted the n by n adjacency matrix in the triangle protocol as a function on 2 log n bits, the GKR protocol interprets the input as a function on log n bits in the same way, exactly the same way. And this final claim that the prover makes at the end of the GKR protocol is just a claim about the multilinear extension of that function evaluated at a random point. And we've already discussed that a verifier can check that claim in linear time.
What would be the probability of mistake, or can the prover really fool you if the verifier, when you send the two values to the top, chooses one and continue just now prove to me this one, and now prove to me this one.
Right, so that's the magic. So what's really happening in this protocol is, I didn't mean to suggest that the prover is actually sending actual gate values to the verifier. In the sum check protocol, what you're dealing with is really low-degree polynomials that are extensions of the gate values when interpreted as functions on bits in the way I was talking about here and with the triangle protocol. So when I say that the prover is making a claim about the value of these gates, what I really mean is it's making the...
If I take the dumb protocol, yeah. The naive dump protocol, you say this is like the computation is equivalent to doing the whole circuit. But if you choose just one branch, it's not the whole circuit.
So here's the problem. So the prover can send like the correct values for like every gate but one here. Okay, and
but there are two values, so it's just
Just saying choose at random.
yes. Okay, so at this layer,
Very small sample.
right?
So 1 over the
Right. Yeah. So the issue is that the soundness error.
Yeah, so what would be the error?
Right.
With what probability you can fit?
Yeah. So at this layer, when there are literally two gates, the soundness error is a half. But eventually, you're going to. This protocol really only gets interesting when the layers get wide.
You have to be right in,
every time.
Yeah. So like imagine if this was a really wide layer, the prover could lie about like just one gate value, and there's very little chance the verifier would detect it. So then you'd have to try to repeat the protocol like an insane number of times to drive the soundness error down, and it doesn't lead to anything interesting.
It sounds like the probability of success will be 1 over n, and
where n is like the circuit size. The circuit size.
The whole size. I mean, the depth is. Let's think of it as log n. In each time you have a probability of success of half.
No, because half only comes in when there are like two gates at the layer. But if a layer had 1 billion gates in it, and the prover sent like all of the right values but one, it can still mess up the output of the circuit, but there's like almost no chance the verifier will pick up on it. So this is the magic of low-degree polynomials, is they amplify even those tiny errors into very easily detectable things. And that's obviously, I mean, maybe this overview can only be so useful without going into the details, but that's the magic of it.
So I guess I don't understand the model. Like the verifier doesn't have to look at the circuit during the verification.
Correct. So, so within the guts of the GKR protocol, you have to use functions that somehow encode the wiring pattern of the circuit. Right? That's like the protocol obviously has to do something, has to depend on the circuit in some way. Otherwise, how are you making sure the prover is dealing with your circuit and not another one? And what's happened, to avoid the verifier materializing the whole circuit, what you need is that these functions that we call them wiring predicates that encode the wiring of the circuit, if you take low-degree extension of those functions, the verifier can evaluate that low-degree extension efficiently. And there's not too much I can really say about this other than like if your circuit is log space uniform, then this all works out very nicely and the verifier doesn't need to materialize the whole circuit and so forth.
But if it's not log space.
Yeah, if it's just some totally wild, ridiculous circuit, then it's hopeless. Like for the verifier to even like really know what circuit you're dealing with, the verifier is going to have to look at the whole circuit. Like how are you even going to write down an arbitrary circuit? You're going to have to write down all the wires.
Doesn't that make the verifier's runtime linear in the sense of the circuit?
Correct. Now that linear step can happen in pre-processing because it doesn't depend on the input. But yeah, the fact of the matter is, if you don't want the verifier to at some point have to spend time linear in the size of the circuit, you need your circuit to have a succinct implicit representation. Right? Otherwise, there's no way to even specify the circuit. Does that make sense?
You're assuming there's a function that describes the circuit.
Right. Yeah. So correct. In GKR's original paper, they showed that for any log space uniform circuit, meaning there's a log space algorithm that can kind of take as input like a label of a wire and tell you what gate it's connecting or something like that, then in fact none of this is an issue. There's basically like a efficient program that represents the circuit in some way, and that's enough to run the GKR protocol without the verifier materializing the full circuit.
So if it's not log space uniform, can I think of it as there's a pre-processing phase that writes down the protocol and the protocol is dependent on the circuit?
Yes. Yeah. So in the pre-processing phase, all the verifier needs to do is evaluate these low-degree extensions of these wiring predicates at a random point, and that's enough. Then it can throw away the circuit. and go ahead with the GKR protocol. And so I guess I need to move on since I'm just about out of time. So hopefully that gives you some sense, just some sense of how it works. So this protocol is efficient for the verifier as long as the depth of the circuit isn't too big, right? So there was communication here between the prover and verifier for each layer of the circuit. So we need the depth of the circuit to be small for the verifier to be efficient. One nice thing about this protocol is we've now achieved a prover that runs in time linear in the size of the circuit. So this is the outcome of a long sequence of works, and the truly linear in the size of the circuit runtime was achieved just this year. Okay, so I want to briefly mention the state-of-the-art general-purpose interactive proof.
When is it truly linear? It's again in this.
In this model with unit cost field operations.
But even like transform it into that. Like how do you even map something to a field?
So the circuit is defined over the field, like the field. Yeah. So the GKR protocol applies to an arithmetic circuit.
I have a question for you. You said that it's used in practice. Where is it used in practice?
Well, I guess it depends what you mean by practice. Tomorrow there will be lots of talks on succinct arguments, and it's now known how to combine the GKR protocol with cryptography to get a succinct argument. And maybe at some point, not too far in the future, people will decide that that argument has, it's like competitive with all these other succinct arguments that people are using some of them in practice various ways. And for specific problems like counting triangles and stuff, if people really were doing that and that's what they cared about, that sum check protocol for counting triangles really is efficient enough for practical use. That doesn't mean people have decided to use it, but they could. Okay. So I hope I have time to tell you this last result. Okay, so what we would really want is the following. So if the verifier asks the prover to run some program on her data, we really want the verifier to not do much more work than read the input, and the prover shouldn't do much more work than run the program. Right? So I defined doubly efficient interactive proofs to just say the prover should run in polynomial time, but really we want the prover to not do much more work than the bare minimum it could possibly have to do, which is run the program. Right? So we really want that if the program runs in time t in space S, the prover runs in time as close to linear in t as possible and space as close to linear in S as possible. And the GKR protocol comes close to achieving this, at least for parallelizable programs, but not in general. Okay, so there's a very nice recent result that comes close to achieving the best we can hope to achieve, which is not this, unfortunately. So for this, you actually need an argument system, which you'll hear about tomorrow. So the key issue is the following. It's that IP is contained in P space. So that is, any interactive proof with a very efficient verifier means that the problem the interactive proof solves can actually be solved in small space.
Yeah, what's n here, sorry?
N is the input size. So in doubly efficient interactive proofs, we want the verifier to run in time linear in n. Okay, so this result, this is called the easy direction of IP equals P space. It says any efficient interactive proof means the problem is solvable in small space. It tells you that you actually can't hope for this to occur. Sorry, the issue is not the prover's runtime, it's the verifier running in linear time. Right? If your problem just requires cubic space to solve, you cannot hope for a linear time verifier in the interactive proof. That's the issue. Does that make sense? This is kind of a technical point. Okay, so what can we hope for? So the best we can hope for is basically if the problem is solvable in like linear space or root n space or n to the 1/3 space, then we can hope for all of this. So Rango, Rothblum, and Rothblum in 2016 came up with a protocol that very nearly achieves this.
Actually worked in science.
I think I knew that, yeah. The crypto program? Yeah. So really, really nice result. And it says the following. So if f is a problem solvable in time t in space S, then, okay, so sorry for the technicality, but we need epsilon to be an arbitrarily small constant. And then we can get the verifier to run in time that's basically linear, plus this power of t, but it's like an arbitrarily small power of t, so you can almost ignore it. And then a polynomial, a fixed polynomial in the space complexity. This is a lot of notation to follow. I'll simplify it in a moment. And then the prover runs in time nearly linear in t, so he's off by just this epsilon factor in the exponent. Okay, so here's, I think, the right way to think about it. Imagine that t was some polynomial in n, say n to the 4th, and s was, I don't know, n to the 1/10. Then we would have a doubly efficient interactive proof system. The verifier would run in linear time, the prover would run in polynomial time. And in fact, the prover is running in time very close to just what the program runs in. Yeah.
What is the trade-off for choosing epsilon small?
Yeah, the trade-off is just the number of rounds is 1 over epsilon. Sorry, exponential 1 over epsilon. So I think if you allowed a super constant number of rounds, you can actually make epsilon subconstant.
The tilde is hiding log n's or log t's or log s or all of the above?
I'll get back to you on that. I think it's hiding log t's.
Does epsilon affect the degree of S in the poly, or no?
I'll have to get back to that. Other questions? So it seems like people are understanding the gist of the result, and I don't know off the top of my head the nitty-gritty details about various dependencies. Yeah, but basically this works for bounded polynomial space algorithms, and the prover is about as efficient as you could hope for. Okay, great. So I guess I can close with open questions, and Ali won't kill me. So obviously, since RRR is kind of the state-of-the-art, if you're looking for generality, the state-of-the-art doubly efficient interactive proof system, there are nice questions about just improving the quantitative nature of RRR. You know, does the number of rounds really need to be exponential in 1 over this epsilon parameter? Can it be polynomial? Do you really need this t to the epsilon? Things like that. So these are technical questions, but this is such a central question. You know, for what problems can we get doubly efficient interactive proofs? That I think these are really important, even if they are technical. Okay. There's also a very nice question about what's called batch verification of NP. So here's the situation. Interactive proofs themselves cannot be what's called succinct. So this means if you're trying to verify an arbitrary NP relation, unless something crazy happens that we don't believe should possibly happen, you can't really do better than just having the prover send the NP witness to the verifier. Okay, so to get succinct protocols, you need to use cryptography, and we're going to hear about that tomorrow. But what you can hope to do is the following. Say I give you k instances of the same NP problem and ask you, so this is like an amortization question, and say, you know, prover, hey, convince me that each one of these k instances is a yes instance. So you could at least hope for like the communication and the verifier runtime to grow sublinearly with k. And it's not known if you can do this or not. So the state-of-the-art result, also by RRR, gives a protocol like this for UP, which is like a subclass of NP, but it's not all of NP. Okay, so I have one parting thought. I promise it's 30 seconds. So in this talk, we've seen some fundamental limitations of interactive proofs. So I mentioned like 2 slides ago, like you just cannot have an interactive proof with a linear time verifier for very space-intensive problems. They cannot be succinct. They're interactive in the name, which makes them unsuitable for some applications. They're not publicly verifiable. So all these things are inherent to interactive proofs. So you might be in this room thinking, well, why should I pay attention to interactive proofs? I need these properties. I need succinctness. I need non-interactive. And I mentioned it already, but I want to be clear. Like these limitations can be addressed by combining interactive proofs with cryptography. I think we're going to hear a little bit about this or related techniques tomorrow. And there are many practically relevant open questions about how best to combine interactive proofs with cryptography that I won't describe, but that's an entire research program that I think is really exciting to focus on this semester for anyone who's interested.
Sure. I have a was just wondering whether the RR protocol, is the core of the protocol similar to GKR, or is it GKR with?
So I can say it does make use of the sum check protocol somewhere in its guts, but it deviates in many ways.
Okay.
You mentioned in the last slide that for the proof you can't be publicly verifiable. You mean public coin, or what?
No, I mean publicly verifiable is like the prover, just publishes a proof, and I guess for this setting to make the most sense, the proof is just a fixed string, so can't even be interactive. And now anyone in the world can come and check the proof.
So that's the previous item of interaction.
So something could be non-interactive and not publicly verifiable. I don't really know how anything could be interactive and publicly verifiable. Do you want to weigh in, Ali?
I mean, like, you could imagine a setting where, like say on the blockchain, sort of the source of randomness comes from some intermediate step, and then so you post a message, then the randomness is revealed to everybody, and that randomness is publicly verifiable, and then you proceed like this for a number of rounds, and then when everything is done, then you have some transcript you can look back and believe, because the randomness was revealed kind of.
There's a paper by Christos, Games Against Nature, right? So this is like an older manifestation of the blockchain idea.
Yeah. But yeah, so they're not sort of verifiable in the sense of just going to active strings you can break down.
Without cryptographic assumptions, like, I mean, when we're talking about proofs, can we have like public verifiability for
Games Against Nature?
If you trust the run.
So I guess to summarize, they're not necessarily the same thing if there's some trusted source of randomness that anyone can verify.
I didn't understand the statement of combining interactive proof with cryptography. Mm-hmm. Well, if you take cryptography to mean that precise complexity, that if you break this, it's equivalent to something that we know what's the complexity. Then it's the same. What's the difference? It's the same theory. It's another algorithm.
Yeah. So I think you're asking about the difference. I think, correct me if I'm misunderstanding, between interactive proofs, which have to be statistically secure. So no matter how hard the prover works to try to trick the verifier, the prover will fail with high probability.
It's probability, yeah.
Yeah.
Probabilistic, yes.
Right. So versus what are called argument systems, which we're going to hear about tomorrow, where you can have something like the following. Like if the prover breaks your crypto system, then he can trick the verifier. Okay. So everything I say here about limitations of interactive proofs, these limitations only come up if it's statistically secure, which is what interactive proof refers to.
I think Justin again will resume at 2.